Welcome back to section 5.6. I just thought it would be healthy to break it into two segments so it didn't get super long in case you needed to refer to one part as opposed to another. So they would like us to write this as a single trig function for the next three. And these are actually going to be the easiest problems that we've done. Now, keep in mind what they're asking us to do is just write it as a single trig function. They're not asking us to do anything more than to recognize what we have. So we would be looking at our formulas, trying to say, who are you? So with this sine over 1 plus cosine, who is that? Who's sine over 1 plus cosine? And that would be tangent of a over 2. So, no problem. We know who this guy is. This is tangent. A in our case is 158.2 degrees divided by 2. So the answer that they're going to have in the back is not some number. They're just going to take half of 158.2 and call it 79.1 degrees, and the answer is tangent of 79.1 degrees. You just wrote it as a single trig function. What about this one? Plus or minus 1 plus cosine of 20 alpha all over 2. Well, hopefully we recognize this as the cosine of an angle divided by 2, right? That one was the plus or minus square root of 1 plus cosine of x all over 2. Well, what's our x? Our x in this case is 20 alpha, and we're going to divide it by 2. So this is the cosine of 10 alpha, and you're finished, right? It's just awareness of the formulas. Who are we dealing with? And then they'll just make sure our arithmetic's okay, because part of the reason for these prerequisite courses is not just to teach you something new like trig, but to review all the old skills. So you know this one. If it's a square root like this, it's either sine or cosine. It has a minus sign, so it's going to be the sine of x over 2. Remember what the sine of x over 2 was. It was 1 minus the cosine of x all over 2. And the whole thing under the square root. Well, that's what we have. So this is really the sine of 3 theta over 5. And then it depends on how you want to look at this. I'm going to write it the way that it stands, over 2. They want to know, are you going to be able to simplify that complex fraction? Because if you leave it like that, you'll get no credit. That is removing all thinking. So you know how to fix that. A few ways to fix that. But hopefully you know that it's just 3 theta over 10. That's what we're hoping, is that you have experience enough with complex fractions from Algebra 1 and Algebra 2 that you're just saying, oh, it's sine 3 theta over 10. Other people would say, oh, this is 3 theta over 5 divided by 2, which is 3 theta over 5 times 1/2, and justify the 10 that way. We need you to come up with the sine of 3 theta over 10. Awesome. You know what's coming next. To wrap up that section, identities that involve these, but also could involve old ones. So what's awesome about the identities as we go on from section to section is that they're not limited to the current section that we're in. They could do anything. So let's take a look at the at this first one, number 48. Sorry. What I think I would do with this one is work both sides independently and show that they're the same. So if I look at sine of 2x, well, I got to remember or look back. The sine of 2x is 2 sine x cosine x. And that's all over 2 sine x. Well, we can see how that simplifies. The 2's go away. The sines go away. This is just cosine x. I need to show this as cosine x. You should recognize cosine squared minus sine squared. Cosine squared minus sine squared was one of the double angle formulas. It was the cosine of, so remember that the cosine of 2 theta was equal to a bunch of things, but one of them, in the base one, was cosine squared theta minus sine squared theta. Not by coincidence, that's what we have. So this is cosine 2 of x over 2. Well, that's the cosine of x. So working them independently, they were the same. We verified the identity. So this is, I don't know if I've modeled that before, working from both sides independently, and then showing that they're the same thing, but that is absolutely a method that can be used. Obviously here I work on the left-hand side and hopefully show the right-hand side. So if I look at this guy, it doesn't look like any trig thing that I've had. It does kind of look like a tangent to 2a, which has a 1 minus tangent squared on the bottom, but this has a 1 plus tangent squared. So I'm not thinking that. I'm looking at the current half angle formula, is not seeing anything. I do recognize that either the top or the bottom is secant squared. So if I look at my identities, hopefully you have the Pythagorean identities either memorized or able to come up with right away. But the Pythagorean identity of, they'll write it like this: tangent squared theta plus 1 is equal to secant squared theta. Well, we have that. We have 1 plus tangent squared. So working from that side, right, I'm going to leave this 1 minus tangent squared x over 2 and realize on the bottom I have secant squared of x over 2. Okay, perfect. Well, how did that help me? Well, now I have a solid denominator. Whenever I have a solid denominator, I look to split it up. 1 over secant squared x over 2 minus tangent squared x over 2 all over secant squared x over 2. Alright, now let's use our fundamental identities. 1 over secant, well, secant's the flip of cosine squared x over 2. And then what about here? Tangent squared is sine squared x over 2, cosine squared x over 2. Secant squared is 1 over x over 2. I'm sorry, 1 over cosine of x over 2. So this is just the cosine squared of x over 2 over 1. Right? So I hope that that was easily followed. So you have, this is your tangent squared, and this is 1 over secant squared, which is what we have on the bottom. The cosines cancel, and we're left with sine squared x over 2. Well, you know about that. Cosine squared minus sine squared is not something arbitrary. If it's the same angle, we know what it is. It's the cosine of 2 times that angle, just like it was a second ago. So this is the cosine of x, which is exactly what we wanted to show, that cosine x was on that other side. So hopefully that made sense. Let me just make sure, if you have tangent of theta divided by secant theta, which is kind of what we had over there, we had, that would be sine theta over cosine theta divided by 1 over cosine theta. We would flip this up and multiply. So we would flip and multiply. So this is sine theta over cosine theta times cosine theta over 1. That's how I got the sine theta. I just took out all the squares and the x's over 2's to help that make sense. Okay, but that's an old trick. We definitely used that before. You should have, at least. And then use the half angle identity. This is actually the first time that we're going to be using a half angle identity, even though this is the section. And it says use the half angle identity to derive the equivalent identity. So they want us to start with tangent of a over 2 is equal to sine a over 1 plus cosine a. Start there, and then show this. Well, if I look at those two things, what I'm noticing is that the bottom has a solid denominator. Okay, let's go get a solid denominator. We could get a solid denominator by applying the conjugate. So what do I mean by the conjugate? Hopefully that's a familiar term. I mean the exact same two terms on the bottom, except with a different sign in between, right? The opposite sign. So what do we have? We have sine a times 1 minus cosine a all over 1 minus cosine squared A. Now you know why we did that. This is sine A times 1 minus cosine A all over sine squared A. Well, one of these sine A's can cancel. So what's that? That's 1 minus cosine A all over sine A, which is exactly what we wanted to show. So sometimes it gets frustrating when you're dealing with identities because you say to yourself, I would have never thought to do that. But that's why we're teaching, right? That's why we're going over examples together. Nobody expects you to know all of the things. So why did I choose this? I knew that 1 minus cosine squared would be sine squared. And I knew I could get that by multiplying the conjugate, right? So that's going to be a common trick. I knew that my top right now had one term, but my top that I want had a two term. So it made sense to multiply by something that had two terms in order to get it. There's no way I'm going to split up a sine A effectively. And again, there could be other ways to do this. But that's what we're looking at here is just creative ways to go through these identities, right? So you're not limited to the identities within each section, and that's the way your test is going to be as well.